chat windows, the channels in my view, but I won't be looking at them constantly because they're a bit out of the way. So we're going to be talking about optics because optics is what makes our telescopes work. Whether it's the biggest Dobsonian telescope in the world, or it's this high-end, well, some moderately high-end astrophotography setup that I found in our Post Your Setup channel, they all have to behave according to the same laws of optics. So it's very worthwhile to understand optics uh, because it's the basis of our telescopes. If you want to understand a telescope, you need to understand optics. Now, as you probably know, there are two major kinds of telescopes. They are reflecting telescopes like this Dobsonian and refracting telescopes like this refractor. And they work on different principles of optics, either refraction and reflection. So we should start by saying a little bit about refraction and reflection. So for refraction, when light um, when light uh, travels from one medium into a different medium, then the effective velocity of the light rays changes, and that will cause the light to bend because the shortest path between this point P and Q is not the straight line from P to Q, but it's in fact this bent line, this curved line, because then the light covers more distance in the medium where it travels faster. And this gives rise to Snell's law of refraction, which relates these angles uh, and the angles with the normal vector, so the vector perpendicular to this interface between the two mediums. So it relates these incoming angle to this outgoing angle as a function of the refractive indices, which are properties of the materials. On the other hand, for reflection, that's a lot easier. For reflection on a straight surface, or on any surface, you just look at the line perpendicular to the surface at the point where the light ray hits, and then the incoming angle must be equal to the outgoing angle. And that's reflection. And knowing these basic laws, we can create surfaces or shapes, either refractive or reflective shapes, that will bend light rays in ways that we want and give them specific optical properties, and specifically for this talk, make telescopes out of them. Uh, and fortunately, we don't actually need uh, to go into detail about these law of refraction and law of reflection to describe what the optical properties of an optical element or a lens or a mirror. We can do that just from geometric or Gaussian optics, or sometimes also called first order optics. It is called first order optics because it is essentially a first order approximation or a lowest order approximation, which is something that physicists love. It is called geometric optics because you can do everything with geometry. So you just draw the light rays and then you can use geometry to figure out where they go. And it is called Gaussian optics because it was pioneered by this man, Carl Friedrich Gauss, which might be a familiar name because this guy has done everything in math and adjacent to math that was remotely interesting, and that includes optics. Uh, and you can actually go one step further than Gaussian optics, and then it's called ray optics, where you drop some approximations that you would make in Gaussian optics, and you just work with like the rays exactly as they work. Uh, there are a number of tools, software tools for that to do the math for you, to work out how the rays will work. One of them you can find online on this link, phidemo.app/rayoptics/simulator, and it can produce images like this one, something that I will also use some examples of in this presentation, starting with right now, uh, because we can lay out the basic optical setup for a telescope. Hello, it should go here. Yes, there we go. So here I have a refracting telescope. These two arrow things are lenses, and you have an incoming beam, and the first lens focuses the light. This is the telescope. The second lens is the eyepiece, and the eyepiece then recollimates the light into uh, a parallel beam again. And this is a very standard diagram for a refracting telescope. Hello, welcome. This is a very standard diagram for a refracting telescope, but it's actually an incomplete diagram because not all of the light that enters the telescope is parallel to each other. Some light rays, in fact, almost all of the light rays, can come in at a certain angle, and they will not be nicely perpendicular to the lens. We'll go more into detail with this later, but you can see as I change the angle of incidence, the point where the light rays focus is different, and also the exiting beam also makes a little angle with the horizontal here. And you can also see that this angle that the exiting beam makes with the horizontal is actually bigger than the angle that the incoming beam makes with the horizontal. We'll go a bit more in depth about this soon, but this is how the telescope magnifies things. So our eye goes here, and our eye now sees a beam of light coming in from this angle, and this angle is larger than this angle. If we were to look at this beam, we would see the light coming from the other direction at a smaller angle. So this image, it looks bigger because this angle is bigger, and it's also brighter because this beam contains exactly the same amount of light as this beam, but it's more dense because this beam is smaller. There's just the same amount of light in less area. And so this will appear brighter than this entire beam, or this whole beam. Now this is for a refracting telescope. We can also make a reflecting telescope. Yes, leaf. That's going to be slightly more complicated, or look slightly more complicated because we need this secondary mirror. This is the Newtonian design, as you probably know, where we have a mirror, a parabolic mirror, and then a secondary mirror that redirects the light, because otherwise we'd have to put our head in front of the incoming beam, blocking most of the incoming beam. And then again, we have here the eyepiece that now recollimates the light. And notice here that this exiting beam has a gap in the middle. This gap is caused, of course, by the secondary mirror being in the way. And this is somewhat important to realize, that there is a gap in this diagram. And again, if I angle this beam, then in this case I'm going to have to be careful not to angle it too much, because then I might miss the secondary mirror, and now no light exits my telescope. That would be pretty bad. This is something that you have to be careful about when you design a Newtonian telescope, is to make this secondary mirror big enough. But you can also see again the angles change correspondingly. So the exiting angle changes as the incoming angle changes, and also the point where the light focuses moves. Now let's go a little bit more in depth about that. Let's go back to the presentation. There we go. And in fact, this is what I would call doing physics. And doing physics is best done with pen and paper. So let's take out some pen and paper, if I don't drop my pens. So in Gaussian optics, what Gauss did to describe these kinds of systems is Gauss said, I don't care about how this lens was manufactured, or how this mirror looks like specifically. I'm going to assume that it was manufactured properly, and that it works the way that we have decided that lenses or mirrors should work. So we're gonna have a box. This is where my camera is. So we're gonna have a box, and whatever's in this box, we don't know and we don't care. This is some optical element, and we're going to describe its properties. And the first of these properties is the optical axis. So there's going to be a line somewhere in the middle of this. That's the optical axis. This, for a telescope, is generally the center of the tube, and that means that this line also points in the direction that the telescope is pointing. Uh, and that's like a reference for the whole system. The second property of the mirror or of the optical element, mirror, lens, whatever, is the focal point. So this is usually labeled F. So let's say there's a focal point. It's on the optical axis somewhere. Let's just put it here. Label it F. This is the focal point. By definition, the focal point is the point where if I have a light beam incoming from this direction, and it comes in parallel to the optical axis, so like this, it's going to enter my black box. I don't know what it's going to do in my black box, but the focal point is defined such that when this beam exits the black box, it's going to pass through the focal point, always. And I can do the same for any beam, whatever distance from the optical axis it is, as long as it's parallel to the optical axis. Then, so I can make a simplification because again, I don't know what's in this box. I don't really care what's in this box at this point of the discussion. But what I can do is I can extend this incoming line as if the box wasn't there, and I can extend this outgoing line as if the box wasn't there. And then they will intersect in some point here. And I can just pretend that all refraction, or well, I guess because the light goes through, this has to be uh, a lens. But I can now pretend that all refraction happens at this point. And I can do the same thing for all incoming light beams again. And all of these points then that I can draw, they will be on a line. And let me draw this in a different color actually. They will be on a line in this diagram. So in reality, this is a plane because this thing is three-dimensional. And this plane is the principal plane, which I will label P. So I can now pretend that all refraction happens in the principal plane, right? Because any light ray that I draw, let's draw a different one. So it enters the box. I don't know what it does, but I can pretend that it keeps going. It hits the principal plane, and then it will be refracted onto the focal point. Now this only talks about rays parallel to the optical axis, and not about rays coming in at any angle, like I just mentioned. Rays can come in at angles not parallel to the optical axis. Before we do that, we have to extend this construction a little bit because this lens is symmetrical. If I have light rays coming in from the other side, the same thing will happen. So there will be a focal point on the other side as well, F, and then there will be an associated principal plane somewhere on the other side as well, P. Let's actually call these P2 and P1 and F1 and F2. So yeah, I'm not going to draw the second light ray, that might get confusing. Usually also in optical diagrams, light comes in from the left. Light that comes in from the right doesn't really exist in the minds of opticians. But we have to consider it for a while to get to the second principal plane. And now there is a third, or a third set of special properties, which are called the nodal points. They are the intersections of the principal planes and the optical axis. And the nodal points will help us with what is happening to light rays that come in not parallel to the optical axis. Because for the nodal points, any light ray that comes in pointed exactly at the nodal point must also exit the lens at the other nodal point in exactly the same direction. So this angle and this angle are now identical. And that lets us make another simplification, namely, we can ignore the entire space between these two principal planes, because light rays that come in from this side are refracted at this plane, light rays that come in from this side are refracted at this plane, and we don't care about what goes on in between them, and we can approximate this lens by a single line. And now, because this is a converging element, usually we add these arrows to indicate that this actually comes from a convex lens. So this is simplification for the convex lens. And these are all the ingredients that we need to trace the image that is formed by the lens. So let's do that as an example. Let's draw the optical axis again, and let's have the focal point right here. We're not going to draw the second one on this side because we're going to have all of the light rays coming in from this side. And now we have an object. Usually people draw arrows for objects. And this arrow, light is going to come from this arrow and is going to be focused by this lens. And we could trace any ray coming from this point, coming from this arrow, but the most useful rays are going to be the one coming from the edge. So the light rays from the edge, there's going to be one there's going to be one light ray that is emitted along the optical axis, so like this. And this light ray is parallel to the optical axis, so we know that after it passes this lens, it must go through the focal point, like this. There is another light ray that is going to be emitted in the direction of the center of the lens, like this. And because the center of the lens, this is where the nodal points are, I should actually label these N, N2, and N1. Because this is where the nodal points are, this thing does not get refracted. It enters this and it exits at the same angle by definition of the nodal points. So it will go here. And now I have to extend this already pretty far to have these intersect, because the image of this thing is going to be formed where these lines intersect. And I'm gonna have to, like, don't mind this kink. I just want to have this intersect without having to go off my paper. So this right here is where they will intersect. And this is where the image of the top of the arrow is. And if we do this for all of the other points on the arrow, then what we find is an image like this, which is much bigger than this image. And so this lens has actually magnified this image. Also notice that this image is not in the focal point. So the focal point is not necessarily the place where the image is placed. It's just a reference point for the system. And now on this figure, we could do some geometry and actually figure out how big this thing is and where this thing goes, depending on how big this is and where this goes, and also the properties of this lens. We're not going to do the details of this because this is much more such a discussion would be more suited for, like, camera lenses, where you care about how far something is. And in astronomy, pretty much everything that we're going to look at with a telescope is infinitely far away. Well, not exactly infinite, but it's very, very, in some sense, very close to infinite. In the sense that the outcome of a calculation that we did based on, like, this distance wouldn't be very, very much different if it was actually infinitely far away. Of course, they are a finite distance away, but that distance is very, very far. Much, much further than the typical focal length of a lens. It's only when you get comparable to the focal length that this distance is actually considered not infinite. We're not going to do the math on that, but I do want to give you the result because just for completion, I suppose. So if this thing is a certain distance away from the lens, and this distance is the object, and then the other thing, let me put that here, then the other thing will be a certain distance, the image away from the lens. So this is the image. There is no object here. This is the collection of focused light beams where you can put a camera sensor and register this image and take a picture in this sense. So this is very relevant for camera sensors or for camera lenses because you have to know like where does the camera sensor need to go depending on this distance. And then it turns out that if you do the math, you can draw some triangles here and rearrange some of the equations. Then you find that the inverse of the object distance plus the inverse of the image distance must be equal to the inverse of the focal length. And this is the thin lens equation. Let me add that. Thin lens equation. This is very useful for cameras, as I said. For astronomy, this object distance, as I also already mentioned, this is very, very big. So the inverse of the object distance is very, very small. If you take 1 divided by a big number, you get a small number. So we can basically ignore this part, and then what we have left is that basically the image distance is equal to the focal length. So for astronomy, for telescopes, our stars and our nebulae and our galaxies are going to form images right at the focal point, but not exactly right at the focal point, because as you can see, this image is still extended. Images aren't made in a single point. This is a whole plane that's right here that has the image in it. And so there's going to be a plane uh, through the focal point perpendicular to the optical axis that is the focal plane. Focal plane. Oops. And this plane right here that the image is in, this is called the image plane. You can't see that. Plane. There we go. And so for astronomy, for telescopes, the image plane is equal to the focal plane, or it coincides with the focal plane, and that's very convenient. But now how do we figure out then how big this image plane is? So we could do a little bit more math on this, but because we know the image plane is going to be in the focal plane, we're going to actually draw a new diagram and go again. So let's draw a lens again, a very straight lens, and the optical axis again. And we're going to have a focal point, as usual. And now for astronomy, our things are infinitely far away. Uh, and that means that unlike in this image, where these points, these light rays that exit this thing, they're diverging. This point emits light rays in all directions. And stars also emit light in all directions. But because stars are so far away, by the time that the light of the stars reaches our telescope, all of the light that goes into the telescope is basically parallel. So all of the light coming from one star is parallel to itself, like in these things. Oops, like in these diagrams that I'm showing here. But stars in different positions, they will uh, emit light in a different direction, and that's where the angle comes in. So let me actually make a second drawing there on the other side here. So if I have a Dobsonian telescope, let me just draw a simple telescope. All right, and this is pointing at the sky along the optical axis right here. And there are stars in the sky, like this. And so this star right here, this star is going to emit light uh, in all directions. And by the time this light enters the telescope, it's all parallel to each other. And because the telescope is pointing right at the star, this light is parallel to the optical axis. But there's a different star right next to this one, here. And this star also emits lights in all directions. And by the time the light from this star enters the telescope, what happens is it makes a certain angle. So it comes in at an angle with the optical axis. And so our goal now um, is to find where the image of this star will go in the focal plane depending on this angle that it makes with the optical axis. Because clearly this light that comes in uh, parallel to the optical axis, this must focus in the focal point by definition. So that's where it goes. It goes in the center of our field. This light that comes in at an angle, as we saw in these diagrams, if we have the light come in at an angle, the position of focus changes and moves. And so we want to know how much it moves. And this we will do the math for because that's relatively simple. Let's go back to the, uh, the first diagram. So we're going to have light come in at a certain angle. And I'm only going to draw one of the light rays that comes in, specifically the one that's pointed right at the center of the lens. Because again, if it comes in at the center, passes through the nodal point, it doesn't move. It doesn't get refracted. And then it hits the focal plane right here. So this is where the image of our star goes. If there's a star like somewhere in this direction, you can't see the star. This star is going to produce an image right here. And the question is, where does this image go? Well, we can draw a very simple triangle, specifically this triangle right here. This triangle. And we're looking for this distance because that's where the image goes. We know, by the way, that that the image must be in the focal plane because the star is almost infinitely far away. So we know from the thin lens equation that the image distance must be equal to the focal length. So it must have an image right here. In this triangle, we can find this angle. This is the incoming angle because this is the angle that the incoming beam makes with the optical axis. And we also know this distance, the focal length. And then this is a very basic trigonometry. That means that this ratio x over f, this depends only on this incoming angle. Specifically, it is the tangent of the angle. If you don't know, you can't read that. Specifically, it is the tangent of this angle. If you don't know what a tangent is, it's a mathematical function that is very useful, and it appears when you look at right angle triangles like this one. This ratio of this side versus this side, or of any two sides, depends only on this angle. And this is how it depends on this angle. Uh, and that's basically how it's defined. And then if we know this function, that means that we can find x as being f times the tangent of the incoming angle. And this is the image scale of my system. Image scale. And this is very useful, especially if you're doing astrophotography, because this tells you how big an object in the sky is going to be. Because sizes in the sky are usually also given in angles. That means that, like the moon, for example, the full moon is half a degree in size. So that means that if you point at one edge of the moon and you point at the other edge of the moon, then the angle between those two directions is half a degree. So this I in this case would be half a degree. You take the tangent of half a degree, you multiply by the focal length, and that's how big the full moon is going to be in your focal plane. And that means if you want to capture the entirety of the full moon in one shot, you need a sensor that's at least this big. Now, that's very useful for photography, but for if we're if we're doing visual observing, then we're going to use an eyepiece. We can't put our eye in here because this is focused light, and our eye doesn't expect focused light. Our eye expects unfocused light, like the beams coming into the telescope, because our eye itself is a lens that focuses light onto the retina, where then the photons are captured and processed by the brain. So that's why we need the eyepiece. We need to convert this focused light back into collimated beams of light so that our eye can then refocus them onto our our retina. And so I would now need to draw an eyepiece to have a complete diagram. But luckily, I don't need to do that because an eyepiece is also an optical element. So it has to basically be governed by the same diagram. So what I can do is this, and now I've drawn an eyepiece. So now we have the focused light from the telescope in the telescope's focal plane. It goes to the eyepiece, and actually, let me add another beam, add another light ray first. So there's going to be more light coming in from the same star, like this, at the same angle. It's going to get refracted, um, and I know how it's going to get refracted because I know its image must be here. So I can now do this. Now let's look at the eyepiece. So we have here the the image that the telescope has formed. The light rays are going to keep diverging out from this image, and then they're going to hit the eyepiece, and the eyepiece is going to recollimate this light, turn it into another parallel beam that exits at a certain angle. And now I'm going to write this in red. Now this angle is going to be O, and this angle is also going to be O. Uh, the focal length is now going to be small f, and the height x is the same because this is the same focused light that entered the telescope. And so this right here, this has to obey the same laws as before. So now we get that the tangent of O is equal to x over f prime. And we can combine this with the other one, which I have here, um, because this x is the same. So x is now equal to f prime times the tangent of O. So that means that f prime tangent of O is equal to f tangent of I. And then the ratio of these tangents, so tangent O divided by tangent I, is equal to f over f prime. And this is the ratio of the focal lengths. And this, as you know, or might know, is the magnification of the telescope combined with the eyepiece. And that's where it comes from. So, uh, so the eyepiece is going to uh, recollimate the light that the telescope has focused, and in doing so, the angle at which the light exits the telescope is going to be bigger than the angle at which it entered the telescope by a factor of m, and this factor is given by the ratio of the focal lengths. Now I say the angle is magnified. Technically, I've written here that the tangents are magnified, but if these angles are small, this is approximately O divided by I. Because in physics, we love our first order approximations. So basically, if these angles are small enough, or if any variable is small enough, then plugging it into any function is going to give you approximately a linear function. So this is something, if O is small, this is something that's proportional to O. If I is small, this is something that's proportional to I. These proportionality factors are the same, so they cancel, and you get O over I. If these angles are big, then this is not really true anymore. But if these angles are big, there's going to be a lot more problems that are gonna make this inaccurate, as we will see later. Uh, because we are under the hood making quite a bit of assumptions here and simplifications here that we're gonna see the effects of later, or we're gonna talk about the effects later. One more thing, I should also apply this linear approximation to this thing right here. So this tangent of I on the image scale, this is going to be approximately uh, pi divided by 180 times the angle of I in degrees. And this is a formula that you will see very often if you look up image scale. They will use, as a consequence, they will use x equal to f pi divided by 180 times the incoming angle I, also in degrees. This is what you will usually find for image scale, and this is fine because the things that you're going to be imaging in astrophotography, their true size or true angular size is not going to be much more than a few degrees. So this is going to be fine. Additionally, this is actually how we've defined that a lens should work. We don't actually want this tangent here. We want a linear function because then things are nicely proportional to each other wherever they are in the image. Otherwise, these proportionalities are going to change um, if things are more to the edge or more to the center of the field. And we don't want that. We want a nice linear image, so we actually want this to be the image scale. So we're going to make our optics more complicated than just a simple optical element, like a simple lens like I've drawn here, uh, to make that work. There is now one more thing that I should then talk about. If we go back to the eyepiece, and it's the diameter here of this exiting beam. This diameter is very relevant. This is, well, the diameter of the exiting beam. This needs to fit into your eye. So if you're doing visual, the beam that exits your eyepiece obviously has to fit into your eye. But your eye pupil has a diameter of only a few millimeters. It's going to be like 7 millimeters on average. It's going to be slightly bigger for younger people and slightly smaller for older people. This is for dark adapted, the dark adapted pupil. In daylight, the eye is about 2 millimeters big for pretty much anyone. Again, that's also an average. So you need to make sure that this beam actually fits into your eye, because otherwise you're wasting light. And the size of this beam, this exit pupil, I was writing eyepiece things in red, so exit pupil, which I'll write EP, this is going to be equal to the diameter of my telescope. Oops, I'm going to write that somewhere else. Uh, the exit pupil is going to be equal to the diameter of my telescope divided by the magnification of my of my my system. And you can also see that from like this diagram. If you have like this is going to be the diameter, then here you have the focal length, and then you turn it around, it's going to become a different beam of a different diameter using a different focal length. And similar to here, what I've done here, the ratio of the two beams is going to be the magnification again. And we can write this out a little bit because magnification is the ratio of focal lengths. So this is the diameter times the focal length of the eyepiece divided by the focal length of the telescope. Uh, there we go. And then we can simplify that into a very useful quantity, which is the focal ratio, which I've written as R, which is equal to, this is not relevant anymore. I'm making a little bit of a mess, I apologize. I should have probably planned this out a bit better. So the focal ratio is the focal length divided by the diameter of the telescope. This is sometimes also called the speed of the telescope. That's the thing relevant for imaging, related to imaging, because a lower focal ratio, as defined here, is a faster telescope. Because if the diameter of the telescope is bigger, then the focal ratio lowers, and the telescope captures more light. So you need less time to get the same amount of light. You need less exposure time to get the same total amount of light. If the focal length of the telescope is bigger, then the image scale of the telescope gets bigger. Let's go back to image scale real quick. then the image scale of the telescope gets bigger. So that means that any object will take more space onto on your focal plane. But the object always gives off the same amount of light. And if it takes up more space on the focal plane, then that light gets divided over a bigger area. And so every pixel in your camera sensor will see less light because the amount of light that is there gets spread out more. And so you have more light if you have a bigger telescope, and you have less light per area if you have a bigger focal length. And the ratio of these two is what determines how fast you can capture something. It's what determines the density of light or of photons on your focal plane. And so this is a very important concept for imaging, and it's also very useful uh, for visual, because you can easily use it to estimate exit pupil. An exit pupil is useful for a few things. Well, firstly, you don't want it to be bigger than your eye pupil. And secondly, you have a ratio here of diameter and magnification. And as most of you probably know, there is a maximum amount of magnification that you can get out of any telescope. And this scales with diameter. So here you have the ratio of the diameter and the magnification. So exit pupil directly is a measure of how big you are magnifying, or how much you are magnifying relative to your aperture, which tells you how much you can magnify. And so in practice, you want this exit pupil to always be bigger than 0.5 millimeters. Always. Because if you look up the rules for limiting magnitude and you plug them in here, you find an exit pupil of 0.5 millimeters. So using this, if you know the focal ratio of your telescope, you can easily estimate what the exit pupil will be of an eyepiece with a given focal length. And then if this is less than 0.5 millimeters, don't buy that eyepiece because it's not going to work. Even if it's already less than 1 millimeter, it's probably not going to be great unless you have like a really, really good scope. And really, really good quality optics. And then also, you should have it be less than 7 millimeter as a guideline, or whatever the diameter of your eye pupil is. If you go bigger, you're losing light. That's one thing. But the second thing is that um, you can actually lose image, kind of. And this is where I said earlier, the hole in our beam that's here is going to become important, because I have here again my Newtonian telescope with its exit beam that has a hole in it. And if this is my eye, then right now I'm not seeing anything. So this light beam, this star that's giving off light that we're directly pointed at, I'm not seeing. Because the only thing that my eye in this position can see is the center of the exiting beam, which isn't there. Now if I move this beam a little bit, then the edge of my field does have something that I can see. So stars closer to the edge, they will be angled in such a way that they can get into my eye. But the center of my field is dark. And this is something that you can see if you use an eyepiece in a very fast telescope, and you use an eyepiece that has a very long focal length, a very fast Newtonian telescope specifically, and you use an eyepiece with a very long focal length, you will see a darkening in the center, and it's because of this, because you're seeing the shadow of the secondary mirror. Now, if this entire beam always fits into your eye, you have no problem, because then you will always see the entire beam, no matter where it is, or no matter how it's angled, and so you don't have this problem. So that's a tip to keep in mind if you're looking to buy eyepieces. Have them be have the exit pupil be between these two ranges, and it's nice to have like a set of ranges in between them, because exit pupil, well, it's the diameter of this beam, and that's also directly related to the brightness of the things. So a bigger exit pupil up until this limit is going to have a brighter image, while a smaller exit pupil is going to have a dimmer image but more magnified. Okay, that was quite a lot, I think. So let's summarize this on this one slide. So we have the focal ratio of the telescope, defined as the ratio between focal length and diameter of the telescope. This is a very, very useful thing to know for your telescope and to keep in mind. Um, we'll also mention focal ratio a bit more later. We have the image scale, which is going to give us the size of an object onto our focal plane, our image sensor, as a function of the incoming angle that it has. We have the magnification. If we use a second eyepiece that has a second focal length small f, then it gives a magnification m, defined as the ratio of the focal lengths. And the beam that exits this eyepiece will have a certain diameter equal to the diameter of the telescope divided by the magnification. This is called the exit pupil, and we can easily find this as the focal length of the eyepiece divided by the focal ratio of the telescope. So um, that's the basic Gaussian optics. But no telescope is perfect, no optical thing is perfect, and to accurately predict what the image will look like, we need to go beyond Gaussian optics. We need to look at aberrations. And I've listed here 7 aberrations that are relevant, or that are generally the first aberrations that people talk about. There are more. There are essentially an infinite amount of aberrations, but they get less and less important. And these will be the most important ones. So they are vignetting, chromatic aberration, field curvature, spherical aberration, coma, astigmatism, and distortion, as you can see over here. And these last 5, they're called the Seidel aberrations, named after this guy right here, Mr. Seidel, because he was the guy who calculated the sizes of these aberrations, or like how severe they are, as a function of the shape of the lens or the mirror. So we named them after him. So let's start with vignetting. Vignetting is actually not really an optical aberration. Uh, it's a loss of illumination at the edge of your field, and it's actually just caused by obstructions um, in your view or inside your telescope. I have a diagram for this. So let's say that we have a simple refracting telescope again, but now there's an obstruction somewhere in my telescope, and this is blocking some of my light. Then, obviously, I will see less light. But also, um, if this light now comes in at an angle, you can see this beam is just not big enough anymore to this beam doesn't illuminate all of this entire aperture anymore. But this beam does. So what you get is that the edge of the field receives less light because this thing is in the way. But the center of the field is unaffected. So you will see this as like a ring, or like just a gradual loss of illumination at the edges. So you're gonna have like a background. If you take like an image, this is mostly visible in imaging. If you take an image, like a picture, and you have like a very bright center, and then it gradually decreases in brightness, in background brightness, as you go out to the edge, that's vignetting. And so this is to be avoided. Now, normally, um, if you have your telescope itself shouldn't vignette. Uh, Most competent telescope makers do make sure that there is no vignetting due to the telescope itself. But it's possible that if you're using something like a diagonal, then maybe the clear aperture of the diagonal is not big enough to actually let all the light in that you want, and so things like that can cause vignetting somewhere in your optical train. There is one more thing here. Even if I remove this, um, there is still going to be some natural vignetting because the finite aperture of the telescope vignettes itself in some way. This is because if a beam comes in at an angle, you can kind of see it, this kind of looks less like it's smaller, this beam now, because it receives less light. If this beam comes in at an angle, the cross section of this beam is not a circle anymore. Like the cross section of this beam that comes in nicely parallel to the axis, this is a circle. The cross section of this beam is an ellipse, and so the light gets spread over a bigger area. But your telescope still has the same area, so it doesn't capture the entire beam in some sense. So there will always, but this is entirely dependent on like the incoming angle of the beam. So for most fields of view, that's not going to be relevant, because most fields of view, again, they're not going to be much bigger than a few degrees, and that's not very. So this doesn't play very strongly. But vignetting inside of your telescope or inside of your optical train, like obstructions like this one, this can definitely be very relevant. And you can actually see like or view the effect that happens when your exit pupil is too big. It's some kind of inverse vignetting. Again, because you're blocking the light or blocking part of the light cone of some beams, but not all beams. Second to talk about of the non-sidal aberrations is chromatic aberration. And this one I have quite a few things to say about, because a lot of what you find about chromatic aberration online is very, very incomplete. There are actually two kinds of chromatic aberrations. But first, what is chromatic aberration? This is something that any basic article on the internet will tell you, that different colors of light will experience different refractive power. So I had the law of refraction here, where this incoming angle and this outgoing angle are related through the refractive indices of the medium. Now, this refractive index actually depends on the wavelength of light. And so that means that the amount of refraction depends on the wavelength of light. And that's a problem because, firstly, the focal length that you experience is different. So the image scale of your different colors is different. So you will have a red object or a blue object being bigger or smaller than the other one. But also, this doesn't only mess with the size of your object, but also with their position. And in this way, you can separate chromatic aberration in two different ways. You have longitudinal chromatic aberration, which talks about the position of your focal point. So effectively your focal length, right? If you refract a certain color more, then the focal length will be shorter and the image scale will be smaller, which usually happens with blue. So here in this example, we have a lot of red dots or red rings that are surrounding our images of our stars, because the red wavelength is refracted less, so has a higher focal length, so has a bigger image scale. And also, it is out of focus, because the position of the focal point or the focal plane depends on the wavelength. So if you're focusing on the blue, then the red will be out of focus. If you're focusing on the red, then the blue will be out of focus. If you focus in the middle, then maybe they will both be acceptably focused, but they will still be slightly out of focus. On the other hand, we can also have lateral chromatic aberration. In fact, these two will generally show up simultaneously, where now the position of the red and the blue images are different depending on the wavelength. And as you can see, longitudinal chromatic aberration, this happens everywhere, so the entire field is unfocused. Lateral chromatic aberration happens at the edges, because everything in the center ends up in the center, but things that are off to the side end up being further to the side or less far to the side, depending on their wavelength. Modern telescopes try to correct for this. Well, firstly, reflecting telescopes don't have this issue because they don't refract light; they reflect light. Refracting telescopes tend to try to correct for this by having more elements with where the variation in refractive index is chosen specifically so that you can focus multiple wavelengths with the same focal length. Um, the cheapest telescopes, refracting telescopes that you can buy, they are achromatic telescopes, and they will try to focus red and blue to the same points. So this, in fact, you could never get because in a real telescope, or unless there are some really, really bad telescopes on the market that I'm not aware of. But you could basically never get because red and blue have the same focal length in pretty much every single telescope that is sold. Some higher end telescopes, refracting telescopes, they will also correct a third color. So they will focus red, green, and blue to the same point. And then you get a pretty good image that is basically free of chromatic aberration. Uh, they are called apochromatic telescopes. The achromatics with two wavelengths, you can see some chromatic aberration in those. Now, the one thing that a lot of articles on the internet will tell you is that this is chromatic aberration. But you should not confuse chromatic aberration with atmospheric dispersion, because the atmosphere also refracts light. And this refraction is also dependent on the wavelength of light. So if you have a bright planet, or any object, the amount of refraction that happens in the atmosphere varies by wavelength. And so there will be a blue planet, a green planet, and a red planet slightly displaced from each other. And this has nothing to do with your telescope. You can see this in a fully reflecting setup. There is nothing that's happening in here that's bad. It's the atmosphere. And this will cause images like this, where you have a blue image displaced from a red image. This is Mars, if you couldn't tell. And very often you will see this being referred to as chromatic aberration, but this, if it's chromatic aberration, it's lateral chromatic aberration, which means that this planet has to be very far to the edge of my field of view in order to even be able to look like this. It's much more likely that this is actually caused by the atmosphere. It is possible that this is lateral chromatic aberration. If you have multiple refracting elements that aren't aligned very well, then you can see something like this. But 99% of the time, this is the cause of the fault of the atmosphere. And I always get annoyed when I see people say that this is chromatic aberration. It's technically caused by the same phenomenon. Like it happens because the the amount of refraction depends on the wavelength of the light. But saying that this is chromatic aberration kind of implies that there is something wrong with this telescope, when in fact it's mostly the atmosphere that's doing this. But that's enough about chromatic aberration. Let's move to the classic sidal aberrations. And first off, we have field curvature, which is exactly what it says it is. It is curvature of the field, specifically the focal plane. So there are these diagrams here. I have some better ones, or some like a simulation that's maybe clearer. Uh, Wait, oh, this is a simulation of chromatic aberration. I almost forgot. So here I have a green beam of light. In and now you can see that this lens, this is not an ideal lens anymore. This is now a real lens. So here I have a green beam of light, and you can see that it focuses here. If I change the wavelength of this beam, then you can slightly see this move. That's the brightness wavelength. Then you can slightly see this move, even more than slightly. And that's longitudinal chromatic aberration. Now, um, if I angle this beam a little bit, let's put this ruler closer, and I now change the wavelength of this thing. I apparently I'm not allowed to click on the canvas. There we go. If I now change the wavelength of this thing, then you can see that the point where it focuses also moves up and down as I change the wavelength, and that's lateral chromatic aberration. So now we're really going to move on. The next one was field curvature. Again, here I have a realistic lens and a beam of light. I can increase the ray density here, probably. And the center of the field is nicely focused. But if I now consider off-axis light, you can see that this is not focused anymore. And now the actual focal point is like here. And if I do this in the other direction, I get the same thing. And that's field curvature. This focal plane, or this plane that I've drawn here, is not the focal plane. The focal plane, in fact, is not a plane. It's not flat. It's a surface. It can have any shape. This shape was first described by Petzval. That's not where I wanted to go. Why? Okay. This shape was first described by Petzval. And so this is sometimes also called like Petzval field curvature. And telescopes that tend to produce a very, very flat field are sometimes called Petzval telescopes. Now you can have positive and negative field curvature, meaning that it can either curve positively or negatively. And then you will have and then so like with the same position of focus, you can have like either the center focused or the edge focused. But you can never have the entire field focused, because focusing, if we go back to the diagram here, if I want this to work properly, I have to align the focal plane of the eyepiece, which also has a focal plane. It has a focal length. It's an optical element. I have to align this focal plane with the focal plane of the telescope. But if the focal plane of the telescope is curved, I can't align the two, because probably the focal plane of the eyepiece is also curved, right? If a telescope can have field curvature, an eyepiece can also have field curvature, and in fact they do have field curvature. So now I'm trying to align two curved surfaces, and that's impossible. And so I can focus those points in the field where they are decently aligned, but then the other points where they're not, I can't. Also, a camera sensor is always straight. It's on a plane. So having a strongly curved field means that my image can never be sharp all across the field, because I'm gonna try to capture this light with a straight camera sensor. This is something actually that's more relevant now than before, because if you're using film, as people did before digital sensors were a thing, you can curve this film. And if you know your field curvature, you can curve your film to fit exactly onto your field. But digital cameras have a lot more advantages than being able to curve. So, and then also being able to have a flat field became more important, and so people actually started making uh, telescopes with a flat field. I believe there are actually some, um, or at least one, professional telescope where the sensor is specifically made to be curved to match the field curvature of the telescope. But you can make telescopes with reasonably flat fields. The next one is spherical aberration. Spherical aberration is the simple fact that spherical elements have no focal point. So this lens right here, this lens has spherical surfaces, and that means that the points where these light rays are focused depend on how far away they are from the optical axis. The colors here, they indicate how far they are from the optical axis. They're not wavelengths, they're not colors of light. But this position of focus now depends on where or how high this ray is in this image, and that's bad, because um, at the start we assumed, or we posited, that the focal point is the point where all light rays must converge if they are parallel to the optical axis. But if you make your optical elements with spherical surfaces, then that's not a thing. And so what you get is you get a defocus all across the field, because nothing can focus. Um, a big problem with spherical aberration is that it's relatively hard to see uh, just by looking at the lens if something is spherical or not. These are two mirrors, two telescope mirrors. One of them is spherical, the other one is parabolic. Now, I don't think anyone in here can tell me which one is which. In fact, not even I can tell because I forgot which one was which. So the only way to tell is by putting them into a telescope and uh, sending light through them. Apparently, I closed uh, this one. That's mildly annoying. Let me open uh, spherical aberration. This one. So here we have these two mirrors again. And now you can see this is the parabolic one. This one nicely focuses all of my light into a single point. This one doesn't. This is the spherical one. Uh, like these don't nicely all intersect in one point. Spherical aberration. No, my laptop is being annoying. Okay, uh, so you really only see this uh, if you like test your mirror. You can't see this visually. That's literally impossible. Uh, and this is one of the things that is more pronounced with faster telescopes. So if you make your telescope faster, the difference between the ideal surface and the spherical surface becomes much bigger, and so your spherical aberration becomes much bigger. This is basically a thing across pretty much all aberrations. If your scope is faster, or your optical element specifically is faster, then the aberration is bigger. It's important that it's the optical element by itself, because you can make telescopes with multiple optical elements, and then you can talk about the focal ratio of the telescope as a whole. But the aberrations, they belong to each element individually, and they depend on the speed of the individual elements. For example, Schmidt-Cassegrain telescopes, they tend to have a very fast primary mirror, and then their secondary mirror magnifies the image by a lot and makes them very, very slow as a whole. But the primary mirror is very fast and so is subject to a lot of aberrations, and these telescopes have to be manufactured relatively precisely in order to actually be good telescopes. So yeah, watch out for telescopes that are very fast and may not be have parabolic mirrors. Next up is another property of the parabolic mirrors, and that's coma. So let's go back to this diagram right here. This telescope, this parabolic mirror, can nicely focus all of the light. But this is only the light that enters my telescope parallel to its optical axis. If I now make this slightly off axis, I defocus again. And this defocus is called coma because it produces comet-like shapes, like this one, like in this example. So in the center of the field, nothing is wrong. But at the edge, you get like a bright head and then like a less bright tail. And this is always pointed towards the center of the field. And this is like somewhat reminiscent of a comet, of the coma of a comet. So this is why we call it coma. And just, it's exactly, well, for reflecting telescopes, for parabolic mirrors, it is basically due to how the mirror works. But it can also happen with lenses. And that's where, Seidel did all of the work to calculate the amount of coma and all of the other aberrations that are in each of these, that are produced by each of these shapes. But it is mostly, or it is best known in reflecting telescopes, but it can also happen in lenses. The thing with lenses is that if you have a refracting telescope, and if you have an expensive one, uh, they can really add as many lenses as they want to correct for as many things as they want. Except, the more stuff you add, the more expensive it's going to get. But they can correct for these aberrations much better, at least, than a mirror can, which is a single optical element. And so you will see this. You will see this in mirrors, or see coma being talked about when the discussion is on reflecting telescopes much more than when the discussion is on refracting telescopes. And then lastly, we have, no, not lastly, right? Not lastly. Second to lastly, we have astigmatism. And now I don't have any more diagrams because now things are getting a bit more complicated. Astigmatism is an asymmetry in the optical path. So what this means is that I now need two diagrams. I need a top view and a side view. So the beam that enters the telescope is a beam. It's three-dimensional. I can look at this from the top and I can look at this from the side. And if these two are different, there is some rotational asymmetry. That means I can rotate my lens and actually have the light pass through it differently uh, than when I don't rotate it. And that's astigmatism. So this is caused by some rotational asymmetry. And this also causes defocus at the edges, either tangential or radial, also called sagittal astigmatism. So you're going to either form lines that are pointing towards the center, or form like lines that are forming circles around the center, or a combination of both. Because all of these things happen simultaneously. Like in physics, we like to break things down into each individual component and talk about the component specifically to understand what's happening for each individual part. But the end result of what you see of any given optic, that's going to be a sum of all of these. And then you just have to figure out uh, which aberrations that are the most severe and causing the most harm to your image. So that's astigmatism. And then lastly, we have distortion, uh, which is again a problem with image scale, or with the focal plane, just a bit similar to field curvature, except now the we're not gonna curve the field, uh, but we're gonna curve the image scale. And this actually goes back to the discussion that we had here when we wrote down image scale, right? This tangent function is not a linear function, and so this causes the image scale of our telescope to not be linear either. Uh, but whenever this is relevant, generally the image scale is not going to be a nice tangent function either, because you're gonna have you're probably gonna have lenses that are um, well, distortion is going to be relevant, and distortion is going to add another complication on top of this, basically. And then also, if you have a refracting telescope, then it might be partially corrected for this, and then it's gonna get even more complicated. And then you really need to know the specifics of the lens, um, like the specific aberration coefficients of the optics that you're using, if you want to accurately calculate the image. But it is a general thing that the image scale for large fields of view is not and can literally not be linear. It literally cannot be linear. You either get positive distortion or negative distortion. Um, and these are sometimes called pincushion and barrel distortion, because if you look at this, you get like a pushed in, like a kind of pincushion shape feeling. If you look at this, you get like a barrel kind of shape or feeling from how these are laid out. And this is mostly going to be visible. This is a thing with a problem with magnification. So you can see here in negative distortion or angular magnification, these points in the center, they're differently spaced than the points in the edge. Actually, that's the same for all of them. Here they're further out than at the edge, and here they're closer together than at the edge. And again, we like our magnification and our image scale to be linear, and so this is seen as a problem, and it is a problem. So we need to correct it. And so people make telescopes and lenses that are well corrected for this. And that's all that I had. Yep, that is all that I had. So we talked about basic optics, about Gaussian optics, and did some math to show how the geometry behind the optics works. And then we moved on from Gaussian optics and looked at aberrations to see how the image is affected by virtue of the optics not behaving as like an ideal lens or an ideal or an ideal mirror.